I think we all have this mental image of a primordial soup, this hypothetical chemical stew where life got its start. But it's always felt so theoretical. Now it seems like we might have just seen one firsthand thanks to data from NASA's Cassini mission at Saturn's moon Enceladus.
It's truly incredible. We are looking at material that has been shot directly out of a subsurface ocean.
So for this deep dive, we're going right into that material, the stuff erupting from those huge cryovolcanic plumes.
That's exactly right. Cassini's final flybys were, just a masterpiece of engineering. It flew through and sampled fresh ice grains straight from that salty global ocean that's hiding under the ice.
And the big reveal.
The big reveal is that we found these previously unknown, really complex organic compounds. It confirms that this moon has this rich, active chemistry, the exact kind of setup you'd need for life's very first steps.
Okay, let's talk about a crucial word you just used, fresh. Why was it so important that Cassini got in so close, just 13 miles above the surface?
Well, because it's the difference between finding an old, weathered artifact and catching something in the act.
Right.
Ice grains that drift out into Saturn's E-ring, they get blasted by space radiation for years. They're altered. But by sampling material just minutes after it erupted, we know what we're seeing is pristine. It's what's actually in the ocean water.
And what are these complex organics telling us? I saw the list of new families. Aliphatic, cyclic esters. That can sound a bit like, just technical jargon. What do these things actually do?
It means we're way beyond simple carbon chains. We have a diverse functional chemical toolkit. Think of them as like the molecular Lego bricks you need.
Okay.
They're the components for building things like cell membranes, for transferring energy. With the nitrogen and oxygen compounds we already knew about, it just confirms this ocean is rich enough to build intricate structures, probably spontaneously.
But where is all this chemistry coming from?
The source is almost certainly hydrothermal activity. Where that massive ocean meets the rocky core, you have heat, maybe up to 90 degrees Celsius, and that's what's driving all these powerful chemical reactions.
This brings us to what's always been the hardest part of the habitability checklist. Enceladus had water, check. Heat, check. Energy and most of the right elements, carbon, hydrogen, nitrogen, oxygen.
CHNO, yep. But the big question mark, the bottleneck, was always the P in CHNOPS, phosphorus.
Exactly. It's the least common of the bioessential elements, but it's absolutely critical for DNA, for RNA, for ATP, which is our energy currency.
And the old models, they suggested it would just be too scarce in these icy ocean worlds. That assumption has been completely overturned.
And this is where the data just becomes, staggering. Cassini found orthophosphates in the ice grains, but the concentration. It's estimated to be at least 100 times higher in Enceladus' ocean than in our own oceans on Earth.
It blows your mind, doesn't it?
How is that even possible? How does this little icy moon manage to concentrate this one critical element so effectively?
That's the beautiful surprise. It seems Enceladus' specific conditions, a very alkaline ocean, probably a pH of 9 to 10.5, interacting with that silicate rock core under pressure, is just incredibly efficient at leaching phosphate minerals right out of the rock and into the water.
So the chemical barrier for life, it's just not there.
It's gone. Which, speaking of efficiently solving complex problems, we should take a moment to thank our sponsor, Embersilk.
Absolutely.
When you're trying to make sense of complex systems, whether it's chemistry on an alien moon or data in your own business, efficiency is everything. If you need help with AI training, automation, or software development, Embersilk is fantastic at figuring out where AI agents can make the biggest impact. You should check them out at embersilk.com.
So circling back to the big picture, the astrobiology implication, we have all 6 essential elements. We have heat. We have a dynamic alkaline ocean. This isn't just potentially habitable anymore, is it?
No. This is a functional primordial soup. It's ready to go. And what's more, the discovery of these diverse carbon-rich compounds, some of which act like lipids, lends huge support to the lipid-first idea for the origin of life.
So instead of needing complex DNA right away.
Exactly. The idea is that basic self-organizing bubbles or membranes form first, just spontaneously, and then the more complex biochemistry evolves inside them. It's a much more plausible pathway.
That is just such an incredibly optimistic outlook. I mean, to find this abundance of phosphorus and complex organics so far from the sun, it feels like Enceladus could be a sort of harbinger for the entire outer solar system.
I think so. It suggests that high phosphorus availability might not be an anomaly. It could be the norm for subsurface oceans out there. It really, really elevates our confidence that the ingredients for life are, pretty much everywhere.
An inspiring thought to end on. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.